Hey, thank you for coming. I'm Todd. I work on Google Cloud Messaging, now called Firebase Cloud Messaging. I focus on performance, specifically reducing battery consumption, improving reliability, and reducing latency. With me on stage is Kieran.
Hi, I'm Kieran, and I work with Todd on the Cloud Messaging Performance team. Today, we're here to discuss some of the details of cloud messaging performance, including how we measure it, some typical latency numbers that we see, some of the factors that can affect that performance, and finally, a few of the cool projects we've been working on lately to help make the service even more robust, especially in the face of unreliable networks. But first, we've had kind of a busy morning, Todd, and I haven't had a chance to talk to you. I saw yesterday that Firebase Cloud Messaging is the new Google Cloud Messaging. Does that mean this whole presentation is out of date?
No, I'm glad you asked. So, as you all heard yesterday, we launched a combined suite of services called Firebase. Firebase Cloud Messaging is the Google Cloud Messaging under that suite. The data that we're going to talk about today applies to both services. Before we get started, I'd like to review a couple basics real quick so we're on the same page. So first, let's look at how a downstream message flows from your servers to the devices. So when it flows from your servers, the first hop is the Firebase Cloud Messaging front end. From there, it's timestamped and persisted to storage. If the device is connected, it's sent immediately to the backend server, where it is then forwarded to the device. So let's take another closer look at the interaction from backend to the device. It's not a simple arrow. The first hop is that it leaves the Firebase Cloud Messaging backend and goes through the internet towards your wireless network or your carrier's infrastructure. Within that point, there's going to be a network address translation device, NAT for short. That allows us to deal with the shortness of IPv4 space. And this is a carrier-provided feature or a wireless network router-provided feature. And from there, From there, it travels to the device. One of the key aspects of this network address translation device is it keeps track of connections. And let's look more closely at how that works. So the connection list is a list of connections and the external IP and ports, along with a timeout. When the timeout expires for the connection being inactive, the connection's removed, and no more communication can happen over that connection. So the devices must reestablish the connection. If that NAT device is really busy, we can run out of space, and we have to evict the least recently used entry before it times out. Most NAT devices are well behaved in that they'll send a TCP reset when they remove an entry from the NAT table, and that will allow the devices to know to reconnect. But some NAT devices don't send a TCP reset. That leaves the connection closed, but the devices are unaware. We call that a silent close. In this scenario, the device must figure out a way to detect that the connection is broken and to reestablish it. One solution for this is to send heartbeats over the connection from the device to our servers. We do this to keep the connections active so that they don't time out and to detect more readily when the connections fail. Another aspect I wanted to review real quick was latency percentiles. As you all know, 50 percentile latency is 50% of latency less than, or 50% of users experience latency less than this metric, and 50% of users experience more latency than this metric. There's also the 80 percentile latency. This is useful for situations where we have a long tail distribution, such as if we're looking at the performance of carrier or Wi-Fi networks, where the performance of individual carriers could vary significantly. In situations where we control more of the infrastructure, such as within our own FCM infrastructure, we can look at 95 percentile latency, which is 19 out of 20 users experiencing less latency than that. So enough review. Let's start with some of the stats. We'll start by looking at latency first. This is the same diagram that you've seen before. We're going to look at, in this next slide, latency from the FCM path. So as the message flows through the FCM servers for both mobile and Wi-Fi. So 50 percentile latency is a small 64 milliseconds. 95 percentile latency is 161 milliseconds. Again, we chose 95 percentile latency here because we control the infrastructure, and so we're able to provide tighter latency bounds. If we're careful, we can estimate the latency. From the FCM, from the point the message enters the FCM infrastructure to the point that it's delivered to the device. To do this, we'll use Google Hangouts data, and we'll use the ACK traveling back from the device to estimate the one-way latency. So 50 percentile latency from the front end of FCM to the client is 160 milliseconds, which is pretty low. 80 percentile latency is 348 milliseconds. We chose 80 percentile here because wireless and mobile networks tend to have a lot of variability in performance, and we felt that 80 percentile latency was representative of a well-behaved network's performance. Oh, sorry. Before I hand off, the data that we've talked about now is for connected devices. Connectivity is an important factor, and Kieran is going to talk about that.
Right. So to give the audience some context, when the team started looking at these numbers, we obviously high-fived ourselves, gave ourselves a pat on the back, et cetera. These are pretty good numbers. But then we took another look, and we realized, like Todd just said, that these are only for devices that already have an active connection with the FCM servers. But there's an entire category of devices that don't have an active connection. And so then the next logical question we asked ourselves was, why? Why don't these devices have an active connection? And is there anything that we can do to make sure that that connection stays open longer and is there more often? And so we didn't really know the answer to that question. So we did what we usually do when we're faced with a question we don't know, which is we looked at the data. And more specifically, we looked at the connection close events that we were seeing. And we roughly categorized them into one of two buckets. And the first bucket is user-initiated connection close events. So these are actions that the user has taken that has influenced their connectivity in some way. So some typical examples that we see here are if the user is worried about their battery or they're not going to see a charger for a while, they might turn off background data. Another example is if the user is going someplace that has poor or limited network connectivity. So that might be the park, the mountains, my parents' house, hi, Dad. Another example that we see is if the user has turned off data by enabling airplane mode. And they could do this for legal reasons, like if they're actually on an airplane. They could also do it for financial reasons or just because they want the noises to stop. So that's an entire category of user-influenced events that can affect somebody's connectivity. And there's a limit to what we can do about those. On the other hand, there's an entire category of external factors that can affect connectivity. Now, the truly pedantic among you may note that this category of external factors is technically pretty close to infinity, right? Like there's a whole bunch of things that can stop a connection between your client and the FCM servers. But that's not really a useful paradigm for us. So instead, we decided to subdivide it into two sections. The first is NAT device issues. So as Todd pointed out, NAT means network address translation. And that's a device that sits between the FCM client, typically an Android device, and the FCM server, and doles out IPv4 addresses and maintains an internal mapping. And typically, the sort of issues that we see from NAT devices are capacity issues or timeout issues. There's also another section here, which is random failures. And these are events that can happen anywhere in the network infrastructure, including power surges and operator failures. And these are things that are difficult for us to account for. There are some steps we can take, but in general, we're pretty limited in what we can do here. So we decided to focus specifically on network address translation issues and see what sort of changes that we could make to make the experience better for more users. But first, we wanted to see how often people were actually affected by NAT issues. So we started to look at the sort of connection close events that we're seeing out in the wild for real mobile operators. And so one of the operators that we looked at had 98.6% of their connection close events being explicit, that is, not silent. Another operator that we looked at had 99.4% of their connection close events being explicit. These are great stats, and we're really happy to see these, because it means that most users, their connections are staying open, or if they're actually being closed, they're being closed explicitly. So both parties know that the connection has been closed, and they can work to reestablish a new one, which means that your connectivity is very high, and you're very likely to get messages very quickly. On the other hand, not all operators are performing at the same level. So here's an example of a small, poor-performing operator that we saw that had almost 40% of their connection closes being silent. That's a huge difference from the other two operators that we saw, so we wanted to kind of dig into what was making this happen and what we could do about it. But first, it may help to go over what exactly a silent connection is and why it's so harmful for us. So here's an example of an explicit close, or what we call a polite disconnect. In this scenario, the device on the left already has an active connection to the FCM servers. So when a message is required to be delivered to the device, FCM sends the message down, it travels through the network infrastructure, the NAT device, and then arrives at the phone in a timely manner. Then the NAT device decides to close the connection, but it sends out an explicit TCP reset or FIN packet to both parties. So now both parties know that that connection has been closed. After a short duration, the Android device attempts to reestablish that connection. It does so, and there's a new connection that is used to transfer data between the Android device and the FCM servers. Then, later, when the FCM servers need to send a new notification down to the device, it does so on the new connection, just like before, and the message is delivered promptly. This is a great scenario because, again, the Android device realizes that the network connection has been closed, so it can reestablish a new one. On the other hand, the silent close events that we see are pretty harmful. So here's an example of one. Again, in this scenario, the phone already has an active connection with the FCM servers. When a message is delivered to the device, it travels through the network infrastructure just like before and arrives at the device. Then, when the router or NAT device decides to close the connection, it does so silently. It doesn't send an explicit packet to either party, so now neither party knows that that connection has been closed. Later, when FCM wants to send a notification down to the phone, it tries to write to that connection, and only then does it realize that the connection has been closed and is unusable. A short time later, the phone will attempt to send a heartbeat back up to FCM, and it will attempt to do so on the old, now dead connection. When it does that, then it will realize that the connection has been closed. It will reestablish a new connection, and FCM will send any messages that have been queued in the meantime back down to the phone. The key takeaway here is that this scenario causes a period of disconnection that can range for up to a couple of minutes between the point of disconnect and until the phone sends a new heartbeat. This isn't a great experience for our users because they can be silently disconnected with no awareness. So if they receive an urgent message, it may not get to them for many minutes. So obviously this isn't a great opportunity, or this is a great opportunity for us to make some changes and see what we can do to fix this. So this is kind of a one weird trick sort of thing. Here's the same poor performing operator. You've already seen this data. Before, almost 40% of their connection close events were silent. After making this small adjustment, almost over 90% of their connection close events were explicit. That's a huge reduction in the number of silent closes that we were seeing. So how did we do this? How do we make this happen? The answer is that we reduced the heartbeat interval to below what we thought their NAT timeout interval was. And so what that means is that when a NAT device typically closes a connection due to timeout issues, it's because it thinks that no data is going to be passed on that connection anymore. An FCM connection, on the other hand, is always active. We're always expecting to receive data on that. That's how you receive your messages so quickly. So the trick here was to make sure that we were sending packets frequently enough that the NAT device realized that the connection was still open and that it shouldn't close it. So here's that same data in a different form. As you can see, for the first 3/4 of the graph, the silent closes over time hover pretty steadily between 1.5 million and just over 2 million. On the other hand, when we initiated the heartbeat interval, or when we adjusted the heartbeat interval, which is that blue dotted line you see the number of silent closes drop dramatically. In fact, they dropped 88% down to just around 250,000. That's a huge, huge improvement, and we're very happy that we got to make that. Now, this approach of taking the whole team and looking at mobile operator data and coming up with a plan and then implementing that plan is great for mobile operators, especially larger ones, where the amount of impact that we can have is dramatic for just that small amount of work. On the other hand, that approach doesn't really scale well with Wi-Fi networks. It's not like I can go in and record each Wi-Fi network and whether or not it's a good quality one. So we had to come up with a different solution. And Todd, I know you have a lot of practice here. Can you give us an example of what we did to make that better?
Yeah. Wi-Fi adaptive heartbeat was a really exciting project for me to work on. We started out with a constant heartbeat interval of 15 minutes. And it was great for most operators, or for most Wi-Fi networks. But there were a few that would be disconnected because they had shorter NAT timeouts than that, or more active devices. A simple solution could be to just reduce the static heartbeat to 4 minutes. But we might consume a little bit more battery as a result. And so what we really wanted was something to develop an algorithm that would balance battery consumption with connectivity. And so we brainstormed on that for a bit and came up with a number of candidates. We took those candidate algorithms and we simulated them against modeled NAT devices. So here's an example. The modeled NAT device varies its timeout in the yellow line. And then the red line shows the heartbeats as they adjust in interval to match that. And that's the Wi-Fi adaptive heartbeat. This simulation here shows that the device was connected over 97% of the time. In comparison, if this same simulation was run with a static heartbeat of 15 minutes, the device only would have been connected 66% of the time. After we refined our algorithm and came up with what we thought was a good solution, we took it to the lab. There we had 4 Nexus 6 devices. We divided them into 2 groups, control group and experiment group. The control group kept the 15-minute static heartbeat, and the experiment group got our new Wi-Fi adaptive heartbeat algorithm. We connected them to Monsoon power meters so we could measure the current consumption of all the devices, and a Wi-Fi network that we controlled. This allowed us to emulate the various NAT behaviors that we had experienced. We also took a TCP dump to verify that the algorithm was operating as expected. From this lab experiment, we came up with some interesting numbers I'd like to share. First, we could compare the cost of doing a heartbeat versus the cost of doing a reconnect. We found that a heartbeat saved 36% battery. A heartbeat consumed 36% less battery than a reconnect. In addition, if we look at a 10-minute NAT timeout device, again, that's one we've talked about before, in the experiment group, it would simply have 2 9-minute heartbeats. In the control group, it would have a 15-minute heartbeat followed by a reconnect. The experiment group, of course, would achieve the 97% connectivity that we had simulated, and the control group would only achieve 66% connectivity. But more interesting is the experiment group would actually consume 3% less battery. And so by increasing the heartbeat interval in certain situations, we're actually able to save battery, in addition to improving connectivity. We started rolling this feature out, and along the way we collected data. I'd love to share with you some of the data we got when we got to the 50% of production users. First, we saw 34% fewer silent closes, and 1% more TTL0 messages delivered. If you remember the GCM spec, time to live 0 messages are messages that are delivered immediately if the device is online, but otherwise they're discarded because they aren't stored to be delivered later. Their time to live is 0. So by delivering more of those messages, that shows that we're connected more of the time. In addition, we improved battery for 54% of users.
Whoa. We improved battery for 54% of users? That's huge.
Yeah, 54%. Thank you. And there's a small caveat to that. For a very small portion of users that were only connected 33% of the time or less, we did spend a little bit of battery. 0.3% more battery consumed for an idle device. So you wouldn't even notice it, but it allowed us to improve the connectivity for that small subset of users 3 times. So in the end, I feel like the battery numbers really paid out. And then the improved connectivity, we improved connectivity for 72% of users. So as a result, this feature is live. Everybody's phone should have it. And we're continuing to think about how to improve it further. In addition to looking at our own data when we rolled out, we also felt it was important to look at data from services that depend on us. So I'd like to look at Google Hangouts 99 percentile latency data. The blue line represents Wi-Fi and mobile users combined. So it's the same. It's both sets of users in one line. And the Wi-Fi line is red. So it's just the Wi-Fi users. So what we can see here is that at the 50% rollout point, the 99 percentile latency for Wi-Fi users dropped. When we got to 100% rollout, the Wi-Fi users continued to drop, but also the Wi-Fi plus mobile 99 percentile users dropped. that means that we've changed what problem is causing the 99 percentile latency for Wi-Fi plus mobile users. In the end, the remaining latency for the blue line was caused by 3G mobile networks, which we focused on later, but that's a talk for another time. If you look just at the Wi-Fi line, we reduced the 99 percentile latency for Hangouts 55%. So we've gone through and looked at how GCM performs, and we've looked at some interesting projects that we really enjoyed working on. I want to take a brief second to talk about what can we learn about the users of GCM from the data that we have. So we're going to look at user-influenced disconnection events. So events where the users decided to be disconnected for a sustained period of time. So we're going to look at events where the user's been disconnected for 30 minutes or more, where they have made the decision not to be reconnected. This is a heat map that I'm going to talk about. One thing I wanted to point out before I started that, though, was that most messages are delivered in well under 30 minutes, but we're only talking about the long tail here. We're only talking about messages that are delivered longer than 30 minutes, or to devices that have been offline for more than 30 minutes. This heat map is color-coded. So red means that a higher percentage of messages are delivered to devices that have been offline, and green represents a lower percentage of messages. We will post on the Spaces app the full set of data for this grid, so you can check it out online. So, for example, 4% of Indian users are seeing their messages delivered to devices that have been offline between 2 and 4 hours. In the US, that's only 0.8%. As you can see, this varies from country to country significantly. Let's take another look at this data in a slightly different representation. This is a cumulative graph. So, for example, you can see here that 15% of users in India, or 15% of messages in India are delivered to devices that have been offline 2 hours or more. 15%. So that means that if you're developing an app for the world, you need to take into account that device connectivity may not be a ubiquitous thing. And so you have to make your app work in a situation where connectivity may go away. And we'll talk more about that in a second. One other data set that I thought we could pull that was interesting is to look at day of the week. This is the global data, so it's not any particular country, but you can clearly see that Saturday and Sunday are days in which the users are less likely to be available on their devices. Maybe they work on the weekdays, or maybe they have phone-free Saturday, Sundays. Kieran, what are some things we can do for users for apps that want to work in an environment where connectivity is not ubiquitous?
I am both glad you asked that question and totally surprised by it. No, I'm joking. So we just released a new open source library. It's called the Firebase Job Dispatcher. And this is a library for scheduling jobs, discrete units of work, on Android and, coming soon, iOS, that let you set constraints and triggers for these jobs. So you can say something like, I'd like to do this download, but only when the user has an unmetered Wi-Fi network. Or I'd like to run this task every week, but only while the device is charging. This helps make sure that your app remains a good app citizen on both iOS and Android. And ultimately, it means that you're respecting your user by making sure you're only using the bandwidth when you absolutely need to. And you're waiting for the most opportune time to initiate downloads or do any maintenance tasks that you need to. This is available right now, and you can check out those links there. The iOS version is absolutely coming soon. We also have a code lab for you called Removing Dependencies on Background Services, and that's available at the link there, g.co/codelab/jobscheduler. We encourage you to check it out. In there, we go over a sample app, and we talk about removing dependencies on background services and converting to this new job-centric world. This is a great way to make sure that your app is more battery efficient and works even better on newer versions of Android and iOS. So this has been us. We've been talking about GCM performance. We'd love to hear your comments and feedback. Please leave us a note in the Spaces app.